Swayam Prabha. Digital India. Educated India.
Welcome. So we are in lecture 15. So here we were studying in this module the axial bar problem and the finite element discretization of axial bar problem. So what I have planned is that here we will continue with the finite element discretization and specially element stiffness matrix, how to construct this element stiffness matrix, and then finally in the last class we have discussed the global stiffness matrix also, but I will just briefly touch upon it and then we will talk about the solution. So let me bring back to that figure that in the last class we are doing. Essentially we were doing a three elements discretization. So I have not discussed about the different nodes and the shape functions and other things. So let us now talk about that how to get the element stiffness matrix of a system or a single element. So before we start, so what we have learned is that this is the finite element discretization. We have learned this, that summation of for a single element node 1 and 2. So that is j equals to 1 to 2 bij uj equals to something summation of j equals to or rather if I and then I just inscribe the sign. So j equals to 1 to 2 phi I xj then qj. So this was the equation that we are talking about. Now in this equation generally we don't represent finite element in terms of bij, rather it's common to represent in terms of kij. So I'm just changing that notation to this is k is nothing but b. So kij uj equals to fi plus summation of j equals to 1 to 2 phi I xj and qj. Now what is qj? We know that this is my q2 and this is my q1. So here we have defined like this, and the coordinate of these points are x1 and x2. So this is my x-axis. Now here obviously each node there are only 1 degrees of freedom because it's an axial problem. So my finite element stiffness matrix which is composed of kij will be something like this that we have discussed in this last class, that is k11, k12, k21 and k22. So how it is coming? Because I runs from 1 to 2. So we have to find out the for each I. So this is a 2 equations for each single element. So it can be any element E. Now, for instance, if you remember the approximation, that approximation was ux was phi I or phi 1 x u1 plus phi 2 x u2. Now, phi 1 and phi 2 are approximating function or finite element shape functions. Now, u1, which is unknown obviously to me, here if you look carefully, that everything is my unknown. We consider everything unknown. u1 is unknown, u2 is unknown, q1 is unknown, and q2 is unknown. So I will when assembling will separate it out. So now first objective is to find out what is the finite element shape functions phi 1 and phi 2. So before we do any of this calculation, so let us now consider a simple 2-node element. Now, what this shape function means? The shape function means how that field variable u, which is deformation or the axial displacement here u, is varying within the element. Now, obviously, it has to satisfy the at u1 or at 1 the displacement is u1, and at node 2 displacement is u2. Now, let us see with a simple approximation. Let us assume that my u varies something like this, a plus bx. So, this is the most common linear polynomial I can think of, and it is also complete because it contains the constant term also. So, now this is a linear polynomial. So, our objective is to find out this ux and find out these two constants. Now, why I didn't consider 3 constants, something like this, ux equals to a plus bx plus cx square. I can choose this also, but this will be difficult because I have 3 constants. Now, I have only 2 conditions that I need to satisfy, u1 and u2 at node 1 and node 2. So, I cannot really evaluate 3 constants. So, from 2 nodes, I can only evaluate 2 constants. So, naturally, if I substitute these conditions, that is u at x1 is a plus b of x1 is actually u1, and u of x2 is a plus b, x2 is my u2. So, now if I write it in this equation in a matrix format, so then it looks like this, 1 x1 1 x2, then a b is my u1 and u2. See, the objective is to find out these constants in terms of u1 and u2. Now, to do that, obviously I have to invert this matrix. So, this is a 2 cross 2 matrix. So, naturally a and b I can find out by inverting this matrix. So, the inversion is very simple, which is x2 minus x1. So, this is the determinant, and then just changing the position and sign. So, x1 goes, this term goes up and this term goes down, and then this is minus x1 and minus 1. So this is my inverse. So this inverse equals to u1 and u2. Now if I multiply, then I will get the constants a, what is a and what is b. So if I get these constants, then obviously I can find out these shape functions very easily. Now for instance, if I write a and b, then it is very simple. A is x2 u1 minus x1 u2 by x2 minus x1, and b is my minus u1 plus u2 by x2 minus x1. So you see the constants a and b can be found out very easily from inverting this matrix. So now my finite element shape functions, how it looks like. So or the finite, and my approximation, how it looks like. My approximation looks like this. Ux is my x2 u1 minus x1 u2 by x2 minus x1 plus u2 minus u1 by x2 minus x1 into x. So these are my a and b, and then x. Now if I rewrite this equation little bit, and if you look carefully, that x2 minus x1 is nothing but this is my x1 and this is my x2. So x2 minus x1 is the length of this element. So this is nothing but, so I can just substitute x2 minus x1 as my LE, length of the element. So I can just take common 1 by x2 minus x1, and then I can write it in this way. So x2 minus x into u1 plus x minus x1 by u2 into u2. So now if I write it in this way, so this is nothing but x2 minus x by x2 minus x1 into u1 plus x minus x1 by x2 minus x1 into u2. Now if you see, look this approximation, then you will see that phi 1 is my x2 minus x1, and this is x2 minus x, x2 minus x, and x2 minus x1, and phi 2 is my x minus x1 by x2 minus x1. So this is my finite element shape functions. Now I can just now choose x2 minus x1 is my LE. So I can just write x2 minus x1 x2 minus x by LE, and then this is x minus x1 by LE. Now I can also choose like this, that my whole element, I can use a different coordinate system and define something, some other coordinate system. For instance, if this is my global x-axis, okay, and then I can define a coordinate system. I can define a coordinate system which starts from here. So here I can define a coordinate system which is contents of x bar. So this x bar, this x bar, if you look carefully, that x1, this is in global coordinate system x, and the x bar starts from 0, and this is x2 minus x1, that is LE. So rather, let me put it in a different color so that it can be very clear. So now I defined a local coordinate system which is x bar starting from node 1 and ending at node 2. So naturally this coordinate system I can transfer it. So how these two coordinate system is related? So simply this is x is actually, I can write x bar plus x1. So naturally at x equals to x2 it becomes x bar is LE. So now if I take the differential, so I can also write this. So there is no x bar here, there is no this is that constant is 1 here. So this is a simple. So this concept is actually extended in case of a Jacobian, in case of a local and global coordinate system, in case of a isoparametric formulation, that we will discuss later. But now if I choose this kind of coordinate transformation, then how my shape function will look like. So naturally my u becomes ux bar. So u is my, now I transfer it in x coordinates, but notice one thing, that displacement at these points doesn't change. These are u1 and u2. So now how my u varies within the element? Within the element, now my u varies as x2 is my x2 minus x is my x2 is my LE. So LE minus x by LE is into u1, and sorry, this will be x bar, and then if I write it carefully, that u2 x minus x bar minus x1 is my 0. So this is LE, right, u2. So now if I write it, this is nothing but x bar by LE into u1 plus x bar minus x bar by LE u2. So this is how my shape function varies within the element. So in case of a dx bar or x bar quantity, I can really transfer it in terms of local coordinate system or local system. So notice here one thing, that this is dA x bar. So that's why we didn't substitute it here. So now if you remember our weak form, that is my Kij. So Kij for a particular element, this was in global coordinate system, it was x1 to x2, then d phi I dx ae d phi j dx into dx. So here I transfer it to x bar coordinate system, which is naturally 0 to LE, and then this also I use the same notation. So phi 1 and phi 1. So this is my phi 1 bar. Yeah, I even I can write it phi 1 bar, but let us say, let us understand that phi 1 x bar u1 and phi 2 of x bar u2. So phi 1 and phi 2 are now in terms of x bar. So naturally my d phi 1, so I am not just changing this thing, but I understand we take this thing that phi I is a function of x bar. Now dx bar obviously, and then this is a d phi j by dx bar and then dx bar. So I can just do this and then find out the stiffness matrix. So first term of the stiffness matrix, if I try to find out, naturally integral 0 to LE, so d phi I by dx, so 1 1. So naturally the derivative of this quantity is minus 1 by LE, so minus 1 by LE, and then AE, this is also minus 1 by LE. So now if I integrate it, this will look like that AE by LE. So if I integrate it, you will find out this is the first term of the stiffness matrix. Similarly, if you do for K22, so that is also we can find out the derivative of second shape functions, so which is 1 by LE. So 1 by LE AE 1 by LE dx. Now dx bar, so this is LE, then this is also AE by LE. Now K12, if I integrate, then how it will look like? Then it will look like that is minus 1 by LE and then AE 1 by LE dx bar, then this will be just simply minus AE by LE, right? Similarly K21, if I do the same thing, and then I will get this thing AE minus 1 by LE dx bar, this is also minus AE by LE. So if I now write it in matrix form, the stiffness matrix of a two-noded bar element, so how it looks like? It looks like this: AE by LE 1 minus 1 minus 1 1. So now you see you have observed this stiffness matrix in case of a matrix method of structural analysis or the stiffness method of structural analysis. But the whole process of finding out the stiffness matrix in within the finite element context is entirely different compared to the that we have learned in the stiffness matrix, stiffness method in structural analysis, where we just use the equilibrium equation that applied force and applied displacement, and then we derive the stiffness matrix. So this is more general in that sense that it not only tells us that how the stiffness matrix will look like, rather it also tells us that how the shape function or how the displacement will vary within the element. So this is one of the major thing that we achieved in finite element procedure. So it tells us everywhere in the element, because if you look carefully now that this element, if I write my phi 1 and phi 2 in this form, then phi 1 is my 1 minus x bar by LE and phi 2 is my x bar by LE. So if I now plot the this thing, if I now plot these shape functions, so how it will look like? So the first thing, that phi 1 will be at x bar equals to 0, it will be 1. So at x bar equals to 0 it will be 1, and at x bar equals to LE it will be 0. So it will look like this. So this at this point it will be 0, and at this point it will be 1, and similarly for phi 2 this will look like this. So you see that at any point this is 1 and this is also 1. So this tells us that how displacement, my displacement approximation, that is u of x bar, is 1 minus x bar by LE into u1 plus x bar by LE u2, how my displacement at this point or any other point varies according to the approximation. So this is the main difference. But if you look carefully, that the derivatives of these functions are essentially constant. If you now take du bar d of ux bar by dx, then if you or dx bar, then you will see that this is 1 by LE u1 plus 1 by LE u2. Now this is nothing but u2 minus u1 by LE. You see, this is a constant thing. So naturally, if I plot the derivative of these functions, so it will look like something u2 and u1 by LE, something like this. So that means if you now go back to the mechanics knowledge of your, then you will see that du dx is my strain. So this is my epsilon x, that is my strain. So strain is constant here. So at this point, so this is so within the element the strain doesn't vary. So because first derivative is constant. So this is how we choose the element as per our requirement, or this is how we do the approximation as per our requirement. Now if you look carefully, that these functions can also be achieved, or these functions can also be found out from a Lagrange polynomial approximation very easily. So if I Lagrange interpolation polynomial, so if I now say what is the Lagrange polynomial? Lagrange polynomial is this Lj of x. So this is product sign. So this so k equals to 1 to n, and then k not equals to j, x minus xk by xj minus xk. So you see this at xj minus means if k equals to j, then this polynomial is undefined. So now here it is assumed that all xi's or xj's are distinct, so both are not same. So now if I just wanted to find out my Lagrange polynomial for this case, so this is nothing but L1, if I write it, then this is nothing but x minus x2 by x2 minus x1. Now sorry, x1 minus x2, x1 minus x2, and L2 is my x minus x1 by x2 minus x1. So now if I write it, is x1 is my 0 and x2 is my LE, then I can just write the phi 1 is my x minus LE by x1 minus x2 is LE. So, minus LE, this is minus LE. So, I can just simply write it 1 minus x by LE. And phi 2 is similar way, I can write it x minus 0 by LE. So, which is x by LE. So, naturally these polynomials, these functions what we have derived here for the stiffness matrix of a bar element, that contains linear Lagrange polynomial. So, similarly we can find out quadratic Lagrange polynomial, cubic Lagrange polynomial and higher order Lagrange polynomial. We will come to that later. But if you look carefully, what is the property of these polynomial functions or the shape functions, then you will see that these polynomial are interpolating polynomial. What do I mean by interpolating polynomial? So, if I take phi I at any point xj of the node point, then it satisfies delta property, that is delta ij property, or sometimes known as cardinal property or Kronecker delta property. What is delta ij means? Delta ij is 1 when I equals to j. So, naturally phi 1 delta ij is defined like this. So, this is 0, this is 1 and this is 0. So, this is when I equals to j and then 0 when I not equals to j. So, which is if you look carefully that at this point phi 1 is 1, that we have seen from by plotting the function, and at this point it is 0. So, naturally it satisfies the Kronecker delta property. So, this becomes an this is known as the interpolation property. And now, if you carefully see that this is summation of phi I at any point is actually 1, and naturally I equals to 1 to n, the order of element or the number of shape functions. Now, this is coming from this property. Now, if I take the derivative, then this property that is I equals to 1 to n, if I take d phi I by dx equals to 0. So, this is also coming from the just simply taking the derivative. Now, the question is how this thing is coming, this summation of phi I x is 1. So, suppose we want to represent a constant field in the domain. So, constant field means that is u1 and u2 does not vary. So, u1 and u2 is x. So, the role of a if you remember my initial approximation, that is u of x is actually a plus bx. So, this constant, because of this constant, it should reproduce the constant solution of the problem. That is why this property is required. So, this is known as the interpolation property. There are two interpolation property, one of this, another of this. This is the consequence of this property. Now, it should able to represent the constant solution. For instance, if I have a simple bar problem where the displacement is constant over the bar, like P delta is PL by AE, that we all say, that homogeneous deformation and all those things, then this should able to reconstruct or able to represent that constant solution. So, that means this, if I choose this property, then if I choose this property, then I can always represent a constant term. So, that is why the complete polynomial including the constant terms is required. So, that is I can write it like this, a to the power 0 plus b x to the power 1. So that's why constant solution is reproduce. So if you look carefully, that finite element solution, finite element shape functions required to satisfy this constant property. Now let us go back to the our force term that we have discussed. The force term here, that Fi, if you remember that Fi, that force term, that is Fi is integral x1, so I will just convert it to 0 to LE. Now this is phi I, and now it is in x bar, and then qx dx. So this was our body force term, that, or the distributed force term. Now if I integrate it, then I will obviously substitute my phi i's, that is f1 is my something like x0 to LE, then 1 minus x bar by LE into, if I take qx as constant, then I can take q out, and then dx bar I can integrate it and find out what is the constant term in the problem. So if I do that integration, which you can easily do it, so this is f1 by f2, so for 2 nodes, then I will get it q LE by 2 1 1. So this is my force term if I do the integration. Then let us go back again to my finite element solution. Now I will write it in matrix form for a single element. So for a single element, my equilibrium equation becomes this is my Ke, which we have derived, then this is my u vector ue, so, and then that is equals to my Fe. So Fe is this, Fe plus my another term is there. If you so let me write it in this form first, and then we'll explain it what it is there. So j equals to 1 to phi I xj q j. Now if you look this term, then you will see that because of the interpolation property, or this property, this first interpolation property, this becomes 1 at x1. So just for this is for I, and this is for I equals to 1 to 2. So there are i's here, so it should be double sum. So anyway, so if I just evaluate it for a single node, that is summation of I equals to j equals to 1 to 2, that is phi I of xj qj. Now if I expand it, then this is nothing but phi, let us say I equals to 1, then phi 1 of xj or x1 qj plus phi 2 of x2, phi 1 of x2 into q2. Now if you see, this quantity will be 0 always because of the interpolation property, because phi 1 is always 0 when I equals to means phi I xj satisfies Kronecker delta property. So and this quantity will be 1, so this will be qj always, or rather q1 here, q1. Now I rewrite this equation I rewrite this equation in this form, that is K E into my UE. So that is equals to my FE plus, now this is my QE vector. So what is my QE vector? That will come later. Now my KE is, we all know what is for truss element or the bar element. What is my KE? KE is 1 minus 1 minus 1 1. Then if I have a constant force, then U1E, U2E, then I have a constant force, I assume a constant body force, then Q LE by 2 into 1 1, and then my QE is essentially QE1 and QE2. So this is my equilibrium equation over the element. Now this in the last class we have seen how to assemble these equations. So for instance, the bar problem that we were doing here, that was this. So there was something, some force was here, and this is constant. Let us take, so this can be very much be function of x or something like that. So let us take Q, and then this is AE and L. Now simply if we assemble it with 3 element, then my this thing, my global stiffness matrix will look like this, that if I take each of the element length same, then this is L by 3, this is L by 3. So let me take the same for computationally easy thing. So let us take, this is L by 3, this is L by 3, and this is L by 3. Now then my stiffness matrix here, it will be 3 will come. So I can just take 3 AE by L, then this is 1 minus 1 minus 1 2, then minus 1 minus 1 2 minus 1 minus 1 1. So this is my global stiffness matrix. So this is my stiffness matrix. Now you see there are 4 nodes. So this is 4 nodes, 1, 2, 3 and 4. So this is my stiffness matrix. I assembled it. Now this is my global stiffness matrix. Now the force vector, if I take that also can be that is global Fe, that is F G global, this quantity. So this can also be if I take L equals to L by 3, then Q L by 6, then this becomes 1 2 2 1. So this is very simple. And then this quantity, that is Qg, that is my unknown reactions at each element, this can also be written in very easy form. So this is my Q1 1 Q. See, remember that the superscript terms coming from element and subscript coming from the node number. So this is Q 1 2, and then Q1 Q2. So this will be added here, Q, because this point is common within element 1 and element 2. So Q 2 1 and then Q 2 2, then that will be again for the third element this will be common. So this is Q 3 1 and then Q 3 2. Now if you look carefully that these quantities we don't know. What we know is that at this point there is a force term. So naturally this quantity will be my P. So this is my reactions, and here also I don't know what is my reactions, so that I need to find out. So naturally this will be there. So here it will be Q11. But at these points there is no point force applied. There is no external loading. Don't consider Q is a point external loading here. Q is an external loading, but it is applied as a body force, not as a point load. So naturally at this point there is no force. So this term must be equals to 0 and this term must be equals to 0. So this term I am just calling it reactions R. So what becomes my QG? QG becomes this, that R 0 0 P. So this is my the whole equation for this bar with 3 elements. Now if I write it, then my 3A by L 1 minus 1 0 0 minus 1 2 minus 1 0 0 minus 1 2 minus 1 0 0 minus 1 1. So this multiplied by U1 U2 U3 U4, because I have 4 degrees of freedom. So now this is equals to this quantity, that is QL by 6 1 2 2 1, then plus this is R 0 0 P. So now I have to solve for this equation. So what are my unknowns? If you look carefully, that unknowns are these degrees of freedom and this reaction. So this is how we generally solve equations that probably you have learned in structural analysis, the matrix method of structural analysis. This quantity is given to 0. So naturally this is my Dirichlet boundary condition. Now in this Dirichlet boundary condition given, so force boundary condition I don't know which is reaction, but on the other hand this displacement we don't know at this point, but we know what is the forces here. So now we can segregate this matrix, and then something like this I can do this. So I can just take this quantity, this part of the matrix this side, and then solve this problem for U2, U2, U3 and U4. So how to do that? So this is my final matrix. This is my 2 minus 1 0 and then 0 minus 1. Sorry, this is minus 1 2 minus 1 and then 0 minus 1 1. So now this equals to summation of this quantity. So this R will not be there. So this I can write it Q L by 3, then Q L by 3, then this will be Q L by 6, then 0 0 P. So this will be my final equation, and I can solve it for inverting this matrix. I can get the solution. So that's the whole idea. Now if you look, I just wanted to tell you one more thing, that if you look the element stiffness matrix, that is Ke. So what was the element stiffness matrix? So that is Ae by Le, 1 minus 1 minus 1 1. So if you find out this stiffness matrix, this stiffness matrix is a singular stiffness matrix. Why it is a singular stiffness matrix? Because if you compute the determinant, determinant is 0. So naturally this matrix cannot be invertible, but this matrix is invertible. Why? Because we have included the boundary conditions. Now here there is no boundary conditions applied to it. On the other hand, in this global stiffness matrix, before I reduce this to a reduced stiffness matrix, this global stiffness matrix, that is the whole this matrix is non-invertible because we have not put boundary condition. So it will move like a rigid body. So that's why the boundary condition is important for the solution. So now this is coming mathematically. So what is mathematical interpretation of it? That stiffness matrix becomes singular unless you put appropriate constraints or boundary conditions. So this will ever you will ever face. You will sometime face that if you are not constrained the structure properly, you cannot really solve it, right? So this will be creating a unsolvable problem unless you constrain the structure. So this is whole thing I wanted to share with you, and now in the next class we'll go for the quadratic shape functions and the some of the other problems that we discussed. So I stop here. So we'll continue with this with quadratic shape functions. Thank you.